Let's now look at multidimensional arrays. First, how do we initialize them? Well, for a matrix in particular, we can choose to write it by column in this way, so the data of the first column, then a space, and the data of the second column, so with two arrays, or we can choose to write it by rows. So the data of the first row, the data of the second row, and so on. In both cases, we obtain the same result. Okay, so how do I define an empty n-dimensional arrays? I can use this syntax, putting attention that what I obtain here is garbage. Inside there is nothing. So this again is we start with something empty and then we add elements. If we want to start with something already, an array with already n elements, for example, here I choose the integer and I choose 3 dimensions, 1, 2, 3, the size of these dimensions, and I can choose with zeros. So here I'm creating an array that has all zeros in the with one column, one row, 2 column, and 3 elements in the third dimensions. The same way I can use it once, and I can use the same syntax I used here with 0, 0, 0, with the number of the size that I want on each dimensions. Again, as before, if I know the element that I want and is fixed, I can use fill to add the same element on all the content, all the element of the array, or I can use random with the number with the size on each dimensions again. A last way to create multidimensional array, and some way used very frequently, is to use list comprehension. We'll see list comprehensions more in details later, but it's pretty intuitive here what it's doing. So here is like we have 4 loops. We are looping over this set here, 1 to 2 for x, between 2 to 3 to y, and between 1 and 2 to zeta, and we create for each values on this nested loop, the output will be given by this expression. So how many, which will be the size, the number of dimensions, and the size on each dimension of this A, of the output of this list comprehension. You can pause if you want. So we have 3 loops, one nested over the other, so there will be 3 dimensions. In the first dimension we have 2 data, in the second one we have again 2 data, and in the third one as well we have 2 data. So our results will be a 2 by 2 by 2 array. And you can see here that you can make very complex structure already with just using this compact syntax. Now you have the array. How do you access the elements of the array? So the basic way is to use commas to separate the dimensions. So if here I have, so let's gonna type it here so we have it. So this is our matrix. I can take the second row, and first column, and I get 5, wait 1 second, second row and first column, and I have 5 here. And here, as I said here, put attention to not confuse the selection you do with a multidimensional arrays where you use comma to separate one dimension to the other, to when you have a nested array that we saw them earlier, where you have multiple square brackets to go deep on each level of the nested array. So you can also use a range to one dimension. So in this particular case, on the second dimension here, so I'm taking here the first row, and then I'm taking the column from 2 to 3. So this 2, 3 here. Here I'm doing the same with a vector, so I'm selecting the position 1 and 3 in terms of row and the column number 1. Or I can also choose to use the full range of the column. So here I'm taking the second row and all the column of the second row. So I'm taking 5, should be 5, 6, 7, and 8, because I'm selecting second row and all the column in the second row. And attention here, because as I am selecting a row, so you may expect that the output is a row. Instead, Julia automatically, as there is only one element on that dimensions, Julia automatically reduce, and as you can see here, we have a standard vector with one dimension. We don't that is represented by a column vector, even if here what we did, we selected a row. So attention about this. Finally, concerning selections, we can use a so-called mask and perform a Boolean selection. So here I'm creating another matrix of Boolean value, true and false, and so on. And I can select my original matrix using this matrix of Boolean values, and the returned value is an array of the elements where this was true. All the functions that we saw for single arrays, well, most of them I assume, works also for multidimensional arrays. But in particular, we have to deal with dimensions. So let's have a look on the functionalities that are related to the dimensions. Size, we already saw it, return a tuple of the size of elements in the different dimensions. We can ask at this point which is the dimensionality of our object, of our array. If A is a matrix, of course the result is 2. So our original matrix is a 3 by 4. We can with reshape we can choose how to reshape our array. In this case, we choose a tensor of 2 by 3 by 2, and of course we have to be sure that the product of the size on each dimension is equal to the total number of elements, or we get an error. Let's go to make another array here. With drop dimensions, we can remove the dimensions conditional to the fact that there is only one element in that dimension. So here I created an array where the second dimension there is only one element. So here you can see that these are actually columns, they are not matrix, so we have only one column on each element. In this case, we can specify that we want to remove the second dimensions with drop dims to be precise, specifying the dimension to drop. If we want to swap our dimensions, we can use Permute dims, and we return a sort of transpose of our matrix. Put attention to the way it is ordered. So here it swap the column with the rows, and if we do the something similar with reshape, actually we have something a little bit different. So we have the same shape, but look what he did here. 159 char. What he did, he take these 3 here, then we said that we want 4 rows, so he put a 2 here, so he did 1592, and then he made the 6, 10, 3, 7, and so on. So these are the same, the result of Permute dims and reshapes has the same shape, but the order where the elements are put is different. Something interesting is the function each slide. So you can loop for each slides, and these return an array, a set of our arrays, so a set of our arrays, an iterator to be precise, that are cut on the dimension that we are going to set, to specify. So here we can see that, so which was here A, let's gonna do it again, type it again here. So our first dimensions, we split our first dimension, that is our rows. So we take first the first row, and here, then we split and we have the second row, and then we split again and we have the third rows. What is interesting here is when we have multiple dimensions, because it's very useful and not easy to do otherwise. So here I'm doing another, okay, here is the case. I'm having a 3x4x2 object, and I'm telling to slice on the first dimension. And you can see here that it is taking as our first result is the result wherever the first dimension is equal to 1, so this one and this one, and then the second element returned by each slice is where the first dimension is 2, so this one and this one, and finally the third element returned by each slice, when I specify that the slice, the dimensions where to slice is the first one, is where the first dimension is 3, so these 2 rows. Often we have the need to flat a vector, that is to reduce n-dimensional array to a single one-dimensional vector. So for this one, we can, for this operation, we can use the keyword vector, or explicitly reshape using only one dimension, or finally using the slice operator. The difference is that these first 2 methods actually do not do not allocate the data again. They just change the information about the container, the shape of the container, while this method here actually, as all slice operation do, allocate new memory to create a new object. Other functionality related to arrays is this vcat that we already saw for arrays. We can use it also for matrix, and it works also for data frames. So here is a vertical concatenation, or we can use horizontal concatenation to join things one column and second column and so on horizontally. If you want to copy something, some array, but we are not interested on the data inside, but only on the type of object and the size of the object, we can use similar, and here the content is metric, so is garbage, so we can but the type is the same, and as well is the size, so we use similar, and then we fill it with data. Of course, there is also a generic cut functions to concatenate on whatever the dimensions. In this case, we have this matrix here, and we can concatenate on the third dimensions here, represented here. So another topic very used, very important, is how to sort elements. We already saw the sort functions, but often you have some data. For example, here, let's gonna type it here. So okay, so imagine that this is our data. We have where we have different fields, and each record is an observation. And we want to sort by the third column, and we want to sort from the biggest to the smallest. So what we can do is we sort permutations of this vector. So here we take all rows of the third column, and we say sort perm instead of sort. It gives us the positions that would sort this vector, and here with this keyword rev we specify the reverse is true, so from the biggest to the smallest. So here we end up with 2, 3, and 1, because 2 is the position of the highest element, 3000, followed by 3, that is 2000, the position of 2000, and finally 1, that is the position of 1000. And at this point, all what we have to do is to use these positions, this vector of positions, as the selections that we want in the dimension of the rows on the first dimension. So here our sorted matrix becomes sorted with the order that we specify. Sometimes we want order by multiple column, but before we arrive here, let's see what is sort slice. Sort slice allows us to sort a slice, as the name say, in this case we sort by column, and we use the first row to do the sorting. If we do here dimension 1, we sort by rows, and we use again the first column to do the sorting. Sort slices, it also has a by keyword that allows to specify the order of the sorting. So in this case, we can specify, so when this sort slice by dimension 1, it take every row, because dimension 1 are the rows, and X become our row. So we take this, if we want the second and the fourth column, we take the element of the row at the second position, the element of the row at the fourth positions, and we use this to do the sorting, and the result is that it's sorted by the second column, so we have 20, but then if you have when these are equal, is go further by the fourth column here. So very powerful sorting. We finished the topic of the vectors and the arrays more in general with an introduction to the basic linear algebra functionality of Julia, but we can access using the linear algebra package in the standard library. So if we have these two vectors, let's gonna make it -1 just to make it more clear something. We can get the transpose in these two ways, either using the function transpose or using a single a single quota. In both cases, we end up with a row vector. And we can take the norm that by default is a P2 level norm. So each element is squared, summed, and take the root square. But we can also specify the level of the norm. So in this case, we take the absolute value and we sum each absolute value. For vector, there are several ways to create vector products. Either we make the inner product, and this take the name also of dot product, and we use dot functions, and we can see here that is the equivalent of taking the first vector as a row. So in this way we transform on a row vector and we multiply by our column vector. Or we can take, in this case, because it's 3 elements, a cross product. What's the problem here? Yeah, this A and B. Or we can take the element-wise product. You can see here that we use in the broadcasting operator that we already saw in the previous segment. Or finally, we can take the outer product, taking the column vector and multiplying by the row vector. Let's now consider a matrix, and you can see that matrix operations are very you can write in very concise way. For example, to make the inverse, you just raise to the power of -1 the matrix. To multiply with it to a power, you just multiply the matrix to a power. You can take the determinant. You can transpose the matrix as well, like we did for the vector. And put attention that transpose like this works only for numerical types. When the matrix contains some other kind of non-numerical types, please use permute dimensions instead. You can take the diagonal of the matrix. And something really useful is the I operator that automatically scale with the needs, and above all, it doesn't create the matrix at all if this one is not really needed. So we can see here that we have a 3x3 matrix, and we multiply by the identity matrix to have a 3x3 to remain a 3x3 matrix. But if our matrix that we want to multiply is a 2x2, our identity matrix here automatically scale to the size where it is used. And finally, concerning vectors, with eigen, we can take at the same time both the eigenvalues that are already sorted and the associated eigenvectors.